Hello everyone, greetings from Ecuador. I'm Lenin Falconi, one of the researchers of paper 42. I'm very glad to be able to share the research that we have done. And I'm making this video in case I don't make it to the IWSSIP 2019 conference. Okay, thanks for the conference and Croatia for letting us present our work. Our paper is based on transfer learning used to classify mammogram abnormalities. We use two models, Mobilenet and Nasnet. The outline for this presentation is presented in this slide. We have 5 points: introduction, the proposed approach, materials and methods, experimentation, and conclusions. Well, just a background, female breast cancer is the most common illness that women have. You can see in the picture that is from GlobalCam. All the pink areas are areas where breast cancer has affected women. And as you can see, it is almost worldwide. Just as a matter of statistics, you have that in 2018, 2 million new cases were reported and 600,000 deaths were due to breast cancer. What has proven to be successful in lowering that risk is early detection. And this early detection is mostly based on mammography, which is the gold standard for screening. However, detection is actually done manually, and it is related to radiology experience. This has been registered as 10% of all women screened to be called back for additional testing. I know this is a drawback in the procedure, since we know that being called for a big C test is something that affects the quality of any one of us. Also in the picture, you can see most of the cancer types that are affecting women according to GlobalCam, and you can see that breast cancer is the one that affects the most. So, since we have a lot of mammographies and we have this thing related to radiologist experience, it's important to use CAD systems to assist the radiologist in the detection process. In fact, these systems can detect sometimes things that are not visible through manual examination. Transfer learning is a deep learning technique that we can use to develop accurate enough classifiers. That is what we are researching in this paper. So our goal was to determine the accuracy of the mass abnormality classification using mainly Mobilenet and Nasnet through transfer learning. We can give it a definition. So this definition is basically the definition of transfer learning. So giving a pre-trained convolutional neural network in a source domain of natural images. These are the images of ImageNet, for instance, and a training source task of classification. In the original papers like Alex Krzyzewski and George Hinton, we know that they classify among 1,000 categories. Transfer learning helps to improve the predictive function of a target domain, which is the mammogram images, using the knowledge that we have in the pre-trained neural network and transferring it to the target task and the target domain. So we have that both domains, the source domain and the target domains, are in fact different. And in fact, in the source task classification, we have 1,000 categories, and in the target classification, we have just 2 categories, benign and malignant. This is represented in this slide as a graphic, where we can see Mobilenet and Nasnet being used in the ImageNet, which has millions of natural images. We make the transfer learning, we adjust the weights of the last convolutional neural networks. Thus, we are able to classify the mammogram images as benign and malignant classes. The dataset that we used in this research was the curated breast imaging subset of DDSIM. This dataset that was published, I think, in 2017. The number of cases between benign and malignant are shown in the slide. As you can see, it's not a lot of data. And also, it's mostly based on DDSM. One of the advantages or benefits of this dataset is that it already has the raw images, which are shown here in the upper part. So we don't have to use any algorithm to extract these masses. We have already those organized in a ground truth table. What's our methodology? We, in fact, from the data set of raw images, we created two data sets. One where we only improved the quality of the image, and then we tested transfer learning on that, and another where we use auto-binarization as an additional step. The image preprocessing is shown in this slide. We merge both training and testing to make just one data set that will be later split for training. It was necessary to normalize the pixel values. Original images have values until 65,535 of grade level, so it's a lot. So we have to scale this into 255. We applied histogram equalization. For resizing, we considered the aspect ratio of the image, which is the relation between the width and the height of the image. Since these pre-trained convolutional neural networks usually use a 224 size of the image, there is a concern about how we should crop and resize the original images. We found that a data set has images that are bigger than 224 and also smaller than 224. In order to preserve most of the information, we use two techniques for upsampling and downsampling, respectively. In upsampling, we use cubic interpolation, and in downsampling, we use area interpolation in order to have the best representation of each picture. But also, we limited our original data to data that has an aspect ratio between the values shown in the equation number 2, 0.4 and 1.5, because images outside these boundaries were too large and really not too wide. So I thought that that could represent a problem when resizing into 224 size, and that we could lose or affect the information that we would need to make a good classifier. In this slide, you have some of these images, and you can see that their height is much bigger than their width, and this affects obviously the classification. So we discarded some examples, they are not a lot, and we stayed with the pictures that were most of the rectangular form where height and width are almost similar. Here we have a previous step of equalization from the original image. That's why you are not seeing it in final 224. But after some steps, the image that is equalized also achieves 224 pixels width and height. This is the steps for what we call the Otsu dataset, where we additionally use the binarization Otsu algorithm and the opening morphological operation in order to reduce breast tissue in the image. Because one of the questions we had was if the image, as it's given by the dataset with the breast tissue and the mass inside of it, will perform better than an image that we can use auto-binarization as a mask extractor and and create this image where we have a black background and the mass is highlighted. So in the research, we were asking, will this be a better image for classification, or will the original Cevis TDSM dataset image just with improvement of histogram equalization will work better? Next, we created our hyperparameters for the training algorithm for both Nasnet and Mobilenet. We use the same parameters. You have 6,000 number of epochs, a batch size of 100, a learning rate of 0.1. The total benign cases and malignant cases are 903 and 772. Data augmentation at this stage was not used. We are currently working on data augmentation, and we're preparing a study where we'll analyze what techniques of data augmentation work better to improve the classification. So it was important for us at this stage not to use data augmentation. Then we have the percentage in which validation, testing, and training sets are created randomly. And for this first stage, we just use accuracy of the classifier. We are now working on using also row cubes and matrix confusion. The results are shown in this table. You can see that for what we call the raw data set, that is the one that has the mass and also the breast tissue, the best model that classified the pictures is ResNet 50. We consider this because we needed to compare Mobilenet and Nasnet with previous works. So in our literature review, we came to the conclusion that Mobilenet and Nasnet have yet not been tested in mammogram images. So we compared that with some other common pre-trained convolutional neural networks. You have that after ResNet 50, you are followed by Mobilenet and Nasnet, and Inception V3 is in the last place. For the Otsu dataset, that is the one with the black background, we have that ResNet is not the best one. Instead of that, the best one with a 68% is actually Nasnet. So we concluded the transfer learning from the natural images domain, which is the source domain, or DS when we check the definition, to the mammogram images is possible. We can achieve an initial accuracy of classification that is good, but the performance is somehow linked to preprocessing that is applied to images. So there is work to do here in improving the images or using even another data sets like InBreast, which is also something we are working now on that we will be publishing soon, because they have full-field digital mammography, which has higher resolution. As I said before, that augmentation is something that we are already experimenting. It was a future work when we presented the paper. And we have what we saw in the last slide, that ResNet 50 is the model that achieved the best accuracy for raw data set. Also, binarization did not improve our classification results, which is a construct with, I think, another work in literature where they use binarization, but they also use another couple of techniques which can be the difference in this result. For them, also binarization helped them to achieve better results. In our case, it seems that for our dataset and our methodology, Otsu is still not helping to have a better classification accuracy. We have like a conflict because ResNet is good for the dataset that has still breast tissue, but it's not good for the one without binarization. Well, I'm very glad to have presented you this research since it's my first work worldwide. And I thank the Congress for letting me explain it to you. And I'm willing to answer any question that you have and receiving any feedback that you can provide. I thank our council so much for being there in representation of us. We had a little problem arriving to Croatia, but we are glad that we can participate. We thank the Congress for being so supporting in this situation. Thank you very much. I'm willing to listen to you.